Today, basically, we are going to talk about the beam designs. So, according to the BS8110, this will be a pre-lecture before you go in for the design classes. The introductions for the reinforced concrete. The reinforced concrete is a composite material that embedded the steel within the concrete section. Basically, the concrete doesn't have a high tensile strength. Rather, they have a good compressive strength. Then the steel bars can resist the high tensile strengths, but will buckle when the subject to the comparatively low compressive strength. So we need to make sure that the concrete is a ductile material. So as concrete is failed to provide enough tensile capacity, we provide the steel within the tensile area to make it stronger to carry out the tensile requirement. So this is how the element is working. So then the steel bars are used in the zone, so within a concrete member which will be subject to the tensile strength. Reinforced concrete is an economical structural material which is both strong in compression and the tension. This is a reinforced concrete, not the concrete. Okay, so I think you probably know the concrete is the second largest material ever used in the world. So next to water. So the concrete is a sustainable material for the human revolutions, industrial revolutions, and also the many support in the advancements of the life. So these materials are being used as a second large use material in the world. The third one is the concrete provide the corrosions, protections, and the fire resistance to the steel bar. So the steel bars, when you put inside the concrete section, you need to make sure that the fire resistance, that if the buildings are subjected to the fire, the enough times to give for evacuate the peoples from the building. So that aspect, so we need to make sure that the steel bars are protected by the concrete. Another one is a corrosion, as Sri Lanka is one of the vulnerable country for the corrosions, has the sea covered all over the country, and the chlorine concentrations within the coastal belt are also significantly high, and wind and the humidity, all these parameters will definitely cover to the problems where the corrosions is. All right. So the basic of design, the two limit state, one is ultimate limit state and the second one is the serviceability limit state. So the ultimate limit state, we talk about the flexure, otherwise we call is a bending. Other one is a shear, and also the tension and the compressions, we used to call it as axial force within the member. So when you design again the ultimate limit state, you need to make sure that all these three parameters to be satisfied before the failure. So your design capacity should be always greater than the available capacity of the element. That's what we call the ultimate limit state. So the serviceability is the one we basically work with the deflections and the crack probably. So these are not the failures actually, probably due to the restrictions of the buildings architecturally and also the people's comfortability. So we need to make sure that all these also within the zone. So one of these, all these first ultimate limit state also to be satisfied, the serviceability limit state also to be satisfied. So this is what we call it as a design process of the reinforced concrete design that you are supposed to learn in the future. So the material properties, I think these fundamentals. So we prefer the compressive strength of the concrete, that probably 7 days, 14 days, 28 days, 28 days, etc. So every week you can have a strength of the concrete, but in a normal, we call the low strength concrete. So let's say the below 50, grade 50. So we refer the grade 28, sorry, the concrete strength is 28 days. And after that, probably still the design concrete strength is 28 days, but probably now that we are talking about the 150 megapascals concrete in the world, we call it a high performance concrete that probably you will earn the 50 megapascal, 80 megapascal within 2-3 days time of the casting. So the two different type of the specimen we use according to the BS8110 for the concrete testing. One is a 100 millimeter cube, another one is a 100 diameter into 200 length, the cylinder. So we mostly work with these cylinder options where concrete is highly, the concrete is measured and the compressive strength. And someone could ask, what are the factors affecting on the concrete strength? Yeah, mostly each and every factors will be affecting, including the weather conditions, the batching plant, the type of the materials, shape of the material, the type of the batching, the way of transporting, curing. So the depending of the technical persons. So all these matters for the concrete compressive strength. So what we need to make sure that we should have to have the good QA and QC policies in the concrete sector, where we need to make sure our concrete, our required strengths to be satisfied at the date, at the place of concrete pouring. So this quality assurance and the quality controls become a key and a critical elements within the reinforced building. So today we are talking about the high strength concrete that you are not going to learn here. But when it is come to high strength concrete, it will be more secured and the quality assurance process will be really need to monitor through the highly technical people. So this is what about the material property. So then let's comes to the definitions of the characteristic compressive strength of the concrete. So what does that mean? It says the once you casted the concrete, so the strength should be within 95% of confident level, or else the 5% of allowable 5% of failure rate are considered for the characteristic concrete. So then you know the bell curves. So normal distribution curve, in other words, in a mathematics you learn it. So after that you take a mean strength. In the concrete mean strength is somewhere here, and the characteristic strength is defined somewhere here. This is what we deal hereafter for the design process. So when it is come to the characteristic compressive strength, because when the questions given to you, when the design start at the industry, so you start with this number and later on you convert it the way you need it for the design process. So the concrete strength class table 3.1, okay, and you can see here if it is C2025, C whatever 25, 30, 28, 35, etc. So the red color shows the cube strength. Okay, so the number 1 shows the cylindrical strength. So if you see mostly the characteristic cube strength FCU are basically here almost refer to the key cube strength in the second column. Okay, you can see. So we work with these numbers to start off with the concrete design. This is the stress strain behavior of the concrete. Okay, so this is a normal stress behavior. It means the cylinder, when you tested the cylinder, the stress strain curve as followed. Then after that, we convert into the idealized stress strain curve that is shown in the BS8110, right? We will come to that points later, where how we deal with this one, etc. Okay, so this curve is we use for design purposes. So we assume that the concrete ultimate strain is 0.0035. You should keep in mind this number as always to make sure that, so what is the ultimate strength of the concrete considered for design process. Let us study the steel behavior, the idealized stress strain curve for the steel. So then there's a one called the elastic region, and after that which is called a plastic region. But you will not even be find these perfectly curved as shown in the figure number 2.2. But what we call is almost the curves are coming like this, and we convert into the two linear zones. So one is the, you can see it is elastic curve, so the inclination is a constant in the first region, and the second one is the gradient is 0. So based on that, two regions we call, one is elastic, another one is a plastic region. So this is what especially the material properties of the steel, and this property, this behavior of the steel make a concrete, purely if you take a mass concrete, that will be ductile material. So however, when we talk about the building, so it should have to have some kind of flexibility, because that here, though you don't study the lateral force combination, so the wind, earthquake, the water, tsunami, snows, there are so many storm, cyclone, so many type of the lateral load which could induce to the building. In such case, there should be a process where the energy is to be disappeared within the building. For that ability, we should have to have a buildings a ductile behavior to ductility behavior. Sorry, brittle behavior to the ductility behavior. So in terms of to transfer the concrete from the brittle to ductile, you need to have some kind of high strain and also high strength material. So fortunately, we do have this steel, the perfectly performing for that aspect. So the durability clauses that you have, you need to refer in the BS8110. So the strength class, the minimum cover, the minimum cement contents, water cement ratios, and the type of cement, the maximum allowable surface crack width. All these to be designed, and also make sure it will be happening in a real batching of the concrete and also the site conditions. Otherwise, so because the design engineer, in the concrete design, the design engineer have been given a freedom to select a strength class, the material, the durability accept. So the water cement ratios, whatever based on his mixed design, all these are flexible to have a design process, but need to make sure that the final is the required design class to be achieved after 28 days. So that is the one we basically do in the mixed design of the concrete. Then the fire protection. So the fire protections of the reinforced concrete members is largely by specifying limit for the normal thickness of the cover to reinforcement, minimum dimensions of the members. So these two basically required any type of the element, including the columns, beams, slabs, so whatever the elements that you are supposed to put in the building, and to be make sure apply in the process of the design. This is concrete cover for the fire resistance. Here you will see the nominal cover, beams, floors, ribs, right? This is called the simply supported beams, the continuous beam, floors in terms of simply supported, continuous, ribs, simply supported, continuous, columns, etc. You might see basically these two columns, the simply supported, are required significantly a high cover in terms of the fire resistance compared to, let's say, in a 3 hours fire resistant, the simply supported beams are required a 60 millimeter cover, and here it's required the 40 millimeter cover. And I said to you before, these fire resistance mean in the, if there is a fire within a building, the building should be evacuate entire people from the locations to outside before it get in failure. So we suppose that this is 3 hours, 4 hours. So that will be depend on the buildings and the number of the occupants, number of the floors, and the time taken down. Because in a fire, you are not advised to use a lift at all. So you should have to have a fire exit, the separate staircase, so or else the different kind of arrangement in the world right now available. So you have to use these passive type of the evacuations to get rid of this fire. So within that region, you need to make sure that the simply supported and the continuous beams wherever you designs are match the requirement of the fire resistance. So you can below read whatever the nodes here, node 1, node 2, all these can be quickly read it out. So but I just wanted to highlight these node A for the purpose of assessing the nominal cover. Nominal cover is the minimum cover for the beams and the columns, the cover to main bars which would have been obtained from the table 4.2, and the table 4.2 has reduced by the nominal allowance of the stirrups of the 10 millimeter to cover the range of 8 to 12 millimeter. So what it says is the real cover, okay, is because once you put the main reinforcement in the columns of the beam, there will be stirrups. Some people use it as hoops, right, to gain the shear strength in the element. So you should basically focus that also, because at that is a part of the steel to make sure to maintain the minimum cover. So what I suggest you is please carefully read entire tables at the home. So the minimum dimensions of the reinforced concrete members for fire resistant, you can see minimum beam width 0.5 etc. So if you take the 3 hours, you can see here 240, the rib width 150, minimum thickness of the floors 150, so etc. So you need to make sure that, right, what is the size of the elements to be placed in the structural design based on the fire resistant. And then when it is come to the concrete columns, it will be a different case, because you know sometimes the concrete columns are being supported by the both side, probably the brick wall, or sometimes in other kind of elements, the retaining wall, let's say it is embedded within the retaining, the concrete columns are formed. So at that time we don't say it's a fully exposed. If the column is fully exposed, sense that so the entire four side of the column has to be exposed to the fire. So you can see then the size of the column width is 400. So the 50%, so it means at least two faces of the columns to be covered by the walls or whatever. So then the required width are getting less. So one face, so still you can see the diameter. So if someone has, despite to fire resistance, so what is the minimum beam width that you can have is a 200. Okay, so the walls also here it has been given, and the minimum reinforcement thicknesses also been given. So this rho means that the percentage of the steel used in terms of the cross section area. So here advise at least to have a 0.4% of the reinforcement area in terms of the area of the columns or the beam. You can see rho is the area of the steels relatively to the uh, concrete. Okay, give me 1 minute. Okay, I think hope you understand up to now everything what we have discussed. So we have discussed up to the fire resistant and the minimum cover selections, etc. Until you see this presentation 2-3 times and you read your books and everything, you not be able to clearly understand the contents within a shorter period of time. So make sure that you put your maximum effort to understand the things what you are listening to me today and even in the afternoon. So the beam, so the beam in the reinforced concrete structures can be defined according to the cross section, positions of the reinforcement and the support condition. Right? Then when it is comes to the reinforced concrete design, the cross section selection is a preference of the engineer. But when you do the economical sectional design, it means always our design should be very fair to the client. It should not be the over design or the under design. So make sure that you see all the lines of the possibility of getting reduce the size of the elements where the minimum requirement of the design has been satisfied. So we have to do some things to our clients where the economical designs to be provided within the structural design. In ultimate design state, the bending is a critical for the moderately loading medium span beam. Shear is a critical for heavily loaded short span beam. In service, a limit state, deflections will be considered. Therefore, every beam must be designed against the bending moments and the shear and the deflection. So this, right now, we have just before talk about the two type of limit state. One is ultimate limit state and another one is a serviceability limit state. When you talk about the ultimate limit state, so the bending, shear and the axial, otherwise compression and the tensions will be considered and it should not be failed in a process of design. The other one is the deflections where the serviceability take place, right? So then the deflection is a serviceability limit state parameter that you to make sure that the buildings within a building are satisfied within the particular deflection. Let us move quickly the type of the beams. One is a rectangular section, other one is a L section, and other one is a T sections. So mostly in your designs, I would like to highlight this times for the level 4, the rectangular sections. We will not talk about much on the T type of sections. So the notations for the beams here you see B and D. D is effective depth. A S is the area of the bottom reinforcement. A S dash is the top reinforcement. D dash is the from the main bars to the top of the reinforcement. So everything has been given in below. So try to familiarize these notations, because after certain point we will only talk in terms of this notation. The design of the building, so the maximum bending moments of the beam, the moment capacity of the section. The moment capacity of the section's beam is affected by the effective depth. That is one of the critical parameter that can increase and the control the moment capacity of the section. The other one is the amount of the reinforcement. Other one is the strength of the steel bar, and other one is strength of the concrete. So all these four parameters are govern a design capacity of the reinforced concrete. So this is a singly reinforced beam. So what does that mean is you can see how the deflection take crack and neutral axis. Neutral axis is the where the compression zone and the tension zones getting merge each other. So you can see here this is the compression, this is a tension. So this somewhere here there is no compression either, no tension. So we call it that line is a tension zone. So here you will see here you will see how you define the, we call it stress block design. So 0.75 times FCU into gamma m. So this is the area where we are calculate as a compress element and the compressive strength of the concrete where it generate against the tensile strength of the bottom. I hope you everyone's understand up to now. So better once again you just quickly have a look on these diagrams, and if you do have any questions type in the chat box. Okay. Okay, quickly we move forward. So this is what it happens, the force equilibrium. So what the forces which is generated from the compression zone is to be equal to the tension force. So this is what the explanation is given here. Moment capacity of the sections M FSCC times Z. Z is the lever arm in between these forces. So then you can here calculate 0.75 because you know that this force is 0.67 times FCU. It's a characteristic step. The gamma m is a safety factor that we are supposed to learn in the future, and this to be equal. The final you will be ended up with this equation. You should be able to derive this equation yourself. Even in the examination, probably I might be asked how to derive these things. So the single reinforcement K is M FCUD and the K dash is M. So if K is less than K dash, then the single reinforcement section is sufficient to resist the moment. Otherwise, the designers has to increase the section size or design the doubly reinforcement. So if this requirement is not being satisfied, either it will be going for the single doubly reinforcement, or else the section depth has to be increased. Okay. Doubly reinforcement, what is in other way around, then the same time you need to put in the reinforcement in the compression zone also. So up here we had considered the tension zone are taking the steel, and the compression forces will counter by only the force generated through the concrete. Then this is what here. then the doubly reinforcements comes. So the sinks mostly this will happen probably the effective depth of the sections you considered for designing the element may not be enough. So then you are not be able to design this. So the beam which contains the tension and the compression reinforcements are termed doubly reinforced. It means in a tension zone and the compression zones both require the reinforcement. So though you see the equations are quite challenging and much complicated, the process is much easy. This is all we derived from the equilibrium equations where we learned from the early levels. Make sure that understand the terminologies and also the fundamental equations that I'm repeating here. Then you applied yourself this equation and try to derive the final equation as shown in below. Then only you will get a confidence what is happening inside the element. So this is what it says. So wherever the tension force is significantly high, that is not be able to counter by the compression zone, you need to put additional steel to increase this compression zone, especially the compression force. So this is what we call the doubly reinforcement beam. So finally the equation is comes like that. Let us find this example quickly. This example is shows simply supported rectangular beams of 7 meter span, carries characteristic loads including the self weight of the beam GK, the QK loads 12 kilonewtons per meter, 8 kilonewtons per meter respectively. Assuming the following material strength, calculate in the area of the reinforcement required. So the FCU is a 30 newtons per millimeter square and the Fy is 500 newtons per millimeter square. So then that is called the yielding steel, yield of the steel. So the newtons per millimeter squared is in the sense that you know the megapascal we referred in the calculation. So the live load and the dead loads, everything is given here. So the live load in the sense that first we talk about the dead load. Dead load is a permanent load probably comes in the building. Let's say the beams of weight of the beams, weight of the columns, weight of the slabs, or else any permanent structures probably coming up on the floors. All these are being calculated under the dead load. So what are the variable loads? So the people come inside the building, so they stay. Then the people probably some movable items we call under the live load. So all these two load has to be considered for the building. But eventually, when you design the high-rise building, there are other types of the loads also come. Wind, then the earthquakes, all these type of loads comes. So then the reinforcement designs might be little bit of complicate rather what you right now doing as a first step. So this is the equation, you know, the safety factor. The safety factor is BS8110. It's referred 1.4 for the dead load. This is what? 1.6 for the live load. So this is the dead load. So you know that the ultimate load is wherever 29.6. And the design moment, you know, if it is a simply supported beam, the design moment is WL squared over 8. So it will be 181.3 kilonewtons meter. So then the K, you can see M FCU BD squared equal to 181.3 10 to the power 6, 30 into 275 into 450. So all these things are the fundamental calculation. You know, if the K dash is we referred 0.156, that's a constant, where the redistribution does not exceed 10%. So this implies the limitations of the neutral axis is almost d over 2. So then here K is lesser than the K dash. So it's a singly reinforcement design, or else we can say in other words, the compression reinforcement is not required. Example 3.2, the singly reinforcement beams Km is equal M FCU BD squared equal 181 into 10 to the power 6. So the FCU is a 30 into 275 into 450. So all this has to be covered because it has to be given in the example. Okay. So the D is given, B is given wherever, right? So then you can find the steel requirement. Simply, this is how you find the main reinforcement within the section. But here you will find the H. But in Sri Lanka, we use it as a T steel. But some people are right now using the high strength because toy steel we are used to have the name before. So there is no issue. Either you use H or the T right now. This is simply the cross sections area of the steel bars, right? So number of the bars are shown here. When you talk about these any bars, you can see, let's say number of the bars. If you take 10 millimeter, 1 by 78.5, so the 5 bars is 550. So as it was given here 1260. So how we put? We have so many ways to put 1260. So look at you can exactly have this one. Even you might find another combination, probably even for maybe if you take this one 7 number of 16, it's all right because the minimum reinforcement requirement has been satisfied. But as an engineer, you need to satisfy there are few other requirements as well. In the future, we will discuss all these things. So the doubly reinforced beam designs are shown here, right? The reinforced concrete beam has an effective span of the 9 meter and the carrying uniform distribution, dead loads, self-load, and the imposed load as shown in the figure below. Design this one. So I will leave it to you. So today you have to make sure that this calculation is done. And I just wanted to see the calculation on the WhatsApp group. So then I would be greatly happy whether you have understand the entire lecture which I have done today. Okay, so this is the one calculations what we need to do, right? Similar thing, right? Nothing more than that. So the same calculation, the design moment calculations, etc. Right? So this is the example number 3. You can calculate yourself. Sorry, and see how these answers are coming or not. Okay. So we have discussed 2 examples. One is here. Okay. And here also it should be WL squared over H2 is missing, right? So then likewise, so before I come to here, I will give you a short break. It's a 5 minutes absolutely. So please be hold here if you want to drink water or something. So quickly do it and come back. Okay. So exactly 5 minutes, and I will take a few times to answer your questions also just after the break. The question is where we can see the practically doubly reinforcement section. So everywhere you can see it. So as engineers, we prefer to have an effective depth. It means the depth of the beams. Effective depth is a different depth of the beams increase, so the automatically effective depth also being increased. So when we do have these limitations for a depth, sometimes due to the architectural purpose, sometimes due to the client requirements, probably the car parking, there are numerous reasons for that. At that time, probably we need to get it sticks to the particular depth. So at that time, so this your sections not be able to meet the singly reinforcement requirements where the K is equal 0.156. Usually it might be increased. So the K is greater than K dash. So then you don't have other options. So you have to go for the W reinforcement. So practically you can see it's actually the depending on your thing. Another question is, I think for the W reinforcement beam, the question how to take the diameter of the compression bar. We have to assume and then have to check and redesign. No, because, okay, let me share the screen right now. Here I said you will find the required area. Then after that, this table, you go there. So you can use 10, here the bar size, 10, 12, 16, 20, 25, 30. So one thing you have to put it, I forget to tell you that. So you don't find a diameter in each and every number. For example, if you want to have a 15 millimeter dia bar, it's not available. This is the unique diameters available in Sri Lanka, also mostly in the world where the British standards comes. So then let's say you required a 510 millimeter square. So let's say 700 millimeter. Okay. So then you have two options. Either you can use 16 diameter 4. Look at. Then a 700 you can put 800. Oils will come here. Here you need to put a 12, now 7 number of 12 bars. The problem is if you put, anyway, if you put the multiple numbers, right? So in a beam section, the section will be mostly congested and the minimum space in between the bars not be able to keep. So that is the reason. So OLs, what you can do is, let's say comes 20, 2 is 600, and so you can put like this, but make sure that you have to provide the minimum requirement, satisfy the minimum. By the way, so number of the bars also, less number of the bars also fine sometimes, because you need to make sure that the spacing in between the bar is greater than the 25 millimeter plus another 10 almost, because the concrete has to go into the down through the reinforcement. So we will come to that point later in the design process, right? Because of this requirement, you have to either check a diameter or number of the bars. I think I had answers all the questions. Okay. So then I think up to now we have discussed about the bending moments designs again, the beams designs again the bending moments. So we call other word the flexural design. If someone asks what is the flexural design, this is also the same we are using. Please keep your mic muted. Okay. So the failure mode of the beam. The failure modes of the beams in the bending depend on the amount of the reinforcement. Under reinforcement, the steel yield and the fail will occur due to the crushing of the concrete. The beam will slowly, considerably deflection and severe cracks, thus provide the warning sign before failure. Then the second one is over reinforcement. The steel does not yield and the failure due to the crushing of the concrete. There is no warning sign and cause, so the sudden collapse. So the over reinforcement sections have a severe issue because it doesn't give the early warning. So it will be quickly collapse. So mostly some people understand only the less amount of steel used in the buildings are getting collapsed, but that is completely wrong, misunderstanding. So what you need to make sure that either low under designs, either over design has to be mitigate, avoid in any type of structural design. The shear failure, what does that mean by the shear? Shear is a two principal shear failure mode. One is a diagonal tension. Inclined crack develops, splits the beams in the two pieces. Shear link should be provided to prevent these failures. The second one is a diagonal compression. The crushing of the concrete, the shear stress is limited to the 5 newtons per millimeter or zero point 0.8 times FCU into 0.5. It means square root of. So if you take a grade 25 concrete, if you put here square root of 25 is a 5, 5 times 0.8 is a 4 megapascal. So either whatever the lowest has to be considered for designing the shear. Let us see the shear equations. The shear stress is determined by the V over BD, shear force due to the ultimate load. B is the breadth of the sections, D is the effective depth. So very easy equation. So once you find it out the shear value, so you can divide it in by the cross sections of the area, then you will get the required shear strength of the beam, available shear strength. So then the shear resistance in the beam is attributed to the number one, concrete in the compression zone. The second one is a aggregate interlock across the crack zones, and the third one is a double action, see the tension of. So here it says, now you find here V, right? So after that, thus the shear resistance can be determined using the calculation of the percentage of the longitudinal reinforced tensions, 100 AS over BD, and the effective depth. So this is 100 AS over VD. So we had discussed now how to find it out the reinforcement. Here if you see, not the entire reinforcement, here you can see it is a or you have to take only bottom reinforcement. Okay, so then the BVD is shown here, right? Then after that you calculate these two, and the effective depth of the sections comes here. So the VC comes wherever, let's say this is the 0.68 value, right? So that value has to be greater than the, less than the available value in the concrete. The values in the tables are obtained based on the characteristic strength of the 225. For the other values, cube strength and all these things, so that can be factored by this one. So it has been written in the down of the table. So if you take BS8110, you will find this table as a table 3.8. So the shear, the value is in the table above are obtained based on the characteristic strength of the 25 megapascal. For the other values of the cube strength is up to the maximum of the 40 megapascal. The design shear can be determined by the multiplied by the value of the FCU into 25. So it's only recommended to go till 40 newtons per millimeter square. The shear, these are the shear conditions. There are three shear conditions, right? The less than the 0.5 times VC throughout the beam. So you can see the note 1, while minimum links to be provided the all beam structure, it will be classified to omit them a member of the minor structural importance such as the lintel or wherever the design shear strength is less than VC. Note 2 is the minimum link for whole length of the beam, 0.5 VC times VC plus 0.4. You can see how it is calculated, the area of the steel, and here you will find the spaces. So all these notations has to be put in your mind. So this is AGV is the one the rate the shear links. Assume that you have a 6 millimeter shear link. So the area of the shear link you can see here minimum links provide a design shear is at 0.4 and then the Fy is yielding strength of the steel. Sometimes we use the mild steel 250, right, etc. So here it comes again the other value, right, in between Vc plus 4 V point this condition, all right. So the you need to make sure that apply this condition where the links only provide. And also there is another one called the bent up bars. So I will be discussing later how it is. It's a different type of approach where high shear capacities can be taken. Usually we put in closest to the column beams joint. All right. So these all notation has to be put in your mind. So the VC, V, everything in this table, right? Then we come see a shear designing. Then the shear stresses exceeding 0.5 VC shear reinforcement should be provided. The vertical shear links, a combination of the vertical and the inclined bars, that is called the bent up bars, right? Now we don't use much on these inclined shear bars. We use basically now vertical bars only. This is what it says, the shear SV, the closest SV is equal to 0.75 times D. ASV is 4 times, it means a total steel area for the one diameter. ASV, where you can put here gross area, right? So if it is a 6 diameter, because you can see two legs are coincide each other, so that single link will give 2 times contribution for the area. So that's why they have put 2 times. So here 4 times. Define the shear reinforcement for the beam using the high list steel Fy 500 newtons per millimeter is for the following load condition: Qk, etc. Qk 10 kilonewtons per meter, Qk 45 kilonewtons per meter. Then you can decide, G. Then you can find it out the shear force here. $100 days over BD from you can find 1.1. So table number 3.1, this one, the effective depth. Then the design of the shear reinforcement. Very easy. You can find it as the ultimate load 1.5 times GK plus 1.5 times in the span 84. So the shear value is, this is a level actually physics, these applied science and the physics. So the reaction is 42 kilonewton. So after that the ultimate shear force comes 42 kilonewton. Then after that 42 divided by 325 by 140, that is 0.425. Okay. This is V into VC over 2, right? 0.2 is less than 0.3, hence the threshold to the shear may not be necessary. So then you have to put the minimum shear reinforcement, because you show here the minimum distance in between the 0.75 times D. Then this is the minimum requirement. Then the diameter, you can select the 1/4 of the main bar, minimum 1/4 of the main bar, or the 6, right? So diameter and the spacing of the links you can calculate as it is. This is a second example. Quickly go through it. 90, so the VBD, so the 0.51. So then according to the table, it will condition number 3. So they provide the normal shear links, right? So the AS over ASV, so the SV, now AC over SV, you can find it out from this 0.3. So after that, the link is paid, SV should not exceed 0.75 time. So 400, so the H8 used as a 300 millimeter. This is what I think the design of the beam is not much critical. And also you can develop your own Excel sheet to calculate these equations, the reinforcement, put into the equations and carry out the calculation. So another example. Okay, so this is what you see here. So design of the shear reinforcement, graded examples are shown here. And even then after that, you can curtail the reinforcement. It means you know that when you draw the shear reinforcement, the maximum shear force is coming at the support. So then from here to here, probably if you can draw the shear diagrams and get the value, reduce the number of the bars, shear links, or else the space. So these two options you would have. Please switch off the microphone. Then the deflection for the rectangular beams, the final deflection should not exceed the span over 250. The deflections after construction of the finishes portion should not exceed span over 500. Right? 20 millimeter, whichever is lesser for span up to the 10 millimeter. Uses approximate method for permissible ratios of the span over effective depth. The cantilever 7, the flange beam 5.6, simply supported 20, etc. So this is the basic span over the effective depth. So this is how it will be finding out. The reinforcement details, the BS8110 spell out a few rules to follow in regards. The maximum and the minimum reinforcement area, spacing of the reinforcement. Then the third one is a curtailment and the anchorage of the reinforcement. Fourth one is the lapping of the reinforcement. I hope you know this word. The maximum and the minimum reinforcement in the sense that in the section, once you selected, comparatively the sections geometry, you cannot put whatever the reinforcement put into the section. There is a maximum and the minimum limit, and also the spacing of the reinforcement. It is the main bars and the shear links, everything. There is a rule for that. Then the curtailment I have just discussed, and anchorage mean how the bars going to the next level, and the lapping of the reinforcement. It means the when you have the two bars, how you kept it. Okay, so the anchorage length is when you curtail the bars, so how you keep the bars away from the anchorage point. This is, I think, some things you have put permanently in your mind. So the minimum number of the bars, whatever. So the 4% is the beams, the rectangular beams. Maximum you can go up to the 4%, and the minimum 0.13. I think you can keep it as 0.13 because we don't use anymore the mild steel for the main reinforcement. Okay. I said to you just before, the minimum spacing in between any bars, tensiles, and the compressions also. So that has to be, you can see H aggregate. So suppose that your aggregate size is a 25 millimeter, then you have to keep additional 5 millimeter tolerance. So that will be 30 millimeter, or else the bar diameter. Bar diameter, let's say the 35. So you have to take as a 35 should greater than the spaces in between the bars, or else 280. The maximum spacing in between two bars is allowed the 1 feet. If you go beyond that, you have to put the additional reinforcement in between. For example, some people designs the deep beams, then those deep beam has to be designs against the under this rule. Sometimes you have to put the redundant bars in between to take care of the shear links geometry. The curtailments, I think I had explained just before. You can see here. So sometimes you no need to, because we designs for the maximum moment. After that, the points where other rounds are getting to 0, or else the lower values. So at that times you can reduce the reinforcement according to the bending moments, drops, and whatever the things in the section. So this is how the curtailment can be done according to the BS8110. Right, you will find these diagrams in your course book, and also the code of practice. So the 100% you have put here because the maximum moment are taken here. So then the point 0.8 L, almost 10%, you can reduce up to the 50%. Right, from here to here you can reduce up to 50%. So then the same things can be done, same things can be done for the continuous beam as well, but make sure that the lengths are shown here. You understand, I think this is we call the sagging movement. You with what you learn in the strength of material, this is sagging movement. The anchorage at the end supports, to achieve a proper anchorage, the tensile bar must extend a little equals to the following: 12 times the bar size beyond the center lines of the support, 12 times the bar size of plus d over 2 from the face of the support. So it has been clearly shown here what is the anchorage length you put where the reinforcement come and curtails at the support. This is what it says. The minimum reinforcement should be put like this. Okay. So this is what it says also, the 4, 5, how the diameter should be done, etc. I don't think the moment analysis and all these to be done. This continuous L and T beams, the analysis to calculate the bending moments and the shear force can be carried out by using moment distribution method. Provide the conditions in the clause 3.4 and 3 of the BS8110 are satisfied, the design's coefficient can be used. So these are the fixed end moment in a ultimate bending moment shear force in the uniformly loaded continuous beam with the approximate equal span. So the moment and the shear force can be obtained from these values, right? L is the effective span, F is the total design load. But you can see here uniformly loaded continuous beams with the approximately equal span. So the load should be equal, and the approximately the span should also be equal. What you need to do is I suggest to do with the structural analysis and get the movement done. So the things will be easy for you to get it. Then the L and T beams are cast monolithically. That is, they are structurally tied. At the mid-span, it is more economical to design the beams and the L or the T sections by including the adjacent areas of the slab. The actual width of the slabs that acts together with the beam is normally termed as the effective flange. So this will be actually in a we don't entertain at your design task, but anyway, if you could just keep it in mind, so that will be helpful in your next level of the design course. I will leave it for your own calculation, right? So that the internal support, the bending moment is reserved, and it should be noted that the tensile reinforcement will occur in the top half of the beams, compressions reinforcement in the bottom half of the beams, right? This is the clause 3.4.1.5, the effective width of the flange beam. So please carefully go through it and learn and keep yourself, but we will not assess in this course. Thank you very much for these listening. 2 hours continuously.